So you're deep in your CUET prep, you're staring at the D block elements, and you can just feel that pressure building. But listen, what if I told you the way most students are studying this chapter is just fundamentally wrong? I mean, be honest. Are you trying to brute force memorize all the trends? Like melting points, atomic size, atomization energy, just as separate facts? If you are, you're playing a losing game. It's exhausting, it's not going to stick, and it's the #1 way to get completely wrecked by a tricky question on the exam. But what if there was a master key, a single core idea that could unlock pretty much every tough question on their physical properties? Stick with me for just the next few minutes, because I'm going to give you that key. We're going to turn all that confusion into total clarity. Let's do this.
Okay, so the reason these elements seem so complicated is actually their superpower. It all, and I mean all of it, comes down to their unique electronic setup, and specifically those powerhouse d-electrons.
Look at this. This is the whole game right here. Your S-block metals, they only use their outer S electrons for bonding. Simple enough. But transition metals? Oh, they bring out the big guns. Because their energy levels are so close, they use both their outer S electrons and their inner D electrons. This little tag team creates ridiculously strong metallic bonds. And that right there is why they have such high melting and boiling points. It's not magic. It's just more electrons getting in on the action.
And that idea of strength leads us straight into another property that trips students up all the time, enthalpy of atomization. But really, it's just another way of measuring the exact same thing we were just talking about.
Just think about it logically. If the bonds holding the metal together are super strong thanks to those d electrons, it's going to take a ton of energy to rip those atoms apart and turn them into a gas, right? That's it. That's all enthalpy of atomization is. A high value is just proof of strong bonds. It really is that simple. Okay, quick gut check. Let's make sure we're on the same page. I'm going to throw some options up. Don't overthink it. Based on what we just said, what's the key reason? Is it A, B, C, or D? Lock in your answer in 3, 2, 1. Yes, it's B. Of course it is. It all comes back to those d electrons joining the bonding party, making that whole metal structure super strong and tough to break. If you got that, you've already got the first part of our master key down. Nicely done. All right, let's hit pause, first attention reset. Time to think about an exception that actually proves the rule. We just said D block elements have strong bonds. So why on earth is mercury a liquid at room temperature? This is a classic question, so let's break it down. And the answer is just brilliant. See, in mercury, those d orbitals are completely full. And since they're stable and full, they barely participate in bonding at all. Without their help, the metallic bonds are way weaker, almost like an S-block element. So the exception isn't an exception at all. It actually proves our main point. Okay, let's shift gears to our next property, atomic size. Now, you'd think this would be a nice, predictable trend, but this is the D block we're talking about. Of course there's a twist that catches so many students by surprise. So the basic idea is pretty simple. As you move from left to right across the period, you're adding more protons to the nucleus. That means the nuclear charge gets stronger. It's like upgrading a magnet. The stronger pull sucks all the electron shells in a little closer, and the atom gets smaller. Makes sense, right? But here's the catch. The atoms don't shrink as much as you'd expect. And why is that? It's because the new electrons are going into the inner d orbitals. And here's the key. D electrons are terrible at shielding. Think of it like a really flimsy curtain that doesn't block the light. They don't do a good job of hiding the outer electrons from that stronger pull from the nucleus. This poor shielding effect is a term you absolutely need to know. And that brings us to our second attention reset. And honestly, this is the biggest, most important twist in this whole chapter. If you can wrap your head around this one concept, you are way ahead of the curve. It's called the lanthanoid contraction. So remember that flimsy curtain from the d electrons? Well, the 4f electrons, which show up just before the 5d series, are even worse. They're like a ripped, totally see-through curtain. They are awful at shielding. This means the nucleus's pull on the outer electrons suddenly gets this massive, unexpected boost. And that powerful pull just yanks the shells of the 5d elements inward, making them shrink way more than they should. And here is the killer consequence for your exam. Because of this contraction, the 5d elements end up being almost the exact same size as the 4d elements, right above them in the periodic table. This is a huge deal. It's why pairs like zirconium and hafnium are called chemical twins. Their properties are incredibly similar. And trust me, examiners absolutely love setting traps based on this idea.
Okay, remember at the beginning I promised you a master key? We've just found all the pieces, so let's put it all together and see how this one idea unlocks the entire D block.
And here it is. It's not 3 different topics. It is one single story. First, the d-electrons jump in to create super strong bonds. That explains the high melting points in atomization energy. Second, the growing nuclear charge shrinks the atoms. And third, the terrible shielding from inner electrons causes the 2 big twists, that gradual decrease across a period, and the massive lanthanoid contraction that makes the 4D and 5D series almost identical in size. See? It's all connected.
So what's the game plan for CUET? First, stop making flashcards of isolated facts. Just stop. Instead, start asking why. Connect every single physical property back to what those d-electrons are doing and the consequences of poor shielding. I'm telling you, if you can explain the lanthanoid contraction in your own words, you are ready for any question they can possibly throw at you. And that's the real secret, isn't it? This way of thinking, it doesn't just work for the D block. So I'll leave you with this question. What other chapter, maybe in the P block, maybe even in organic chemistry, is giving you trouble because you're just memorizing facts instead of looking for that one core underlying principle? Go find that master key and you'll unlock your rank. Good luck.